Welcome to the 1975 Nobel Prize in Physics, which went to Ben Mottelson, Leo Rainwater, and Aage Neils Bohr, son of the actual Niels Bohr. That might be a Nobel laureate if you look at the back catalog of stuff. Okay, he is. Okay, but um, this particular discovery concerned a connection between collaborative motion of particles inside the atomic nuclei, and it's kind of a development of the theory of how the atomic structure inside the nucleus actually fits together. So it's not the overall atom. We're just dealing with just the nucleus and how that works in this one. And the nucleus consists obviously of neutrons and protons, which we refer to as nucleons. And before this work, it was assumed that the nucleus was kind of spherical or in a teardrop shape or like a drop of water. But this work showed that was just absolutely had to be wrong. Um, and the nucleons themselves in the outer part can move around. In the inside, they're a little bit different. So you have these valence shells versus inner shells of the nucleon, and we'll get into all that. Now, this was interpreted and figured out, in the 50s, but it did take a while for this prize to come along because if you look at the back catalog of prizes we've been going through, there's been quite a few of them that were really, really interesting stuff. This is absolutely shockingly interesting if you're a nuclear physicist, but it did take a while for this prize to come to fruition, 23 odd years. But it was accepted into the community very quickly because the fit with theory was just too good. So let's dig in a little bit and see what all that gobbledygook is actually telling us. Now, during certain parts of the 1940s, there was this sort of global research on nuclear physics because of what was going on in World War II. So it's sort of the second half of the 1940s. Things like the Manhattan Project were taking place, and that's not including all the work the Axis were doing. So Germany had their own program, everybody did, and they were massive. Tons of money was spent. Lots of people were looking at this, but it still only gave us kind of this fuzzy picture of what was really going on inside the nucleus. We kind of knew a few tricks. We knew a few things we could do. We could split it. We could kind of figure that out, and that worked. But as you saw in the movie Oppenheimer, they split the atom in a way everybody was going, well, that shouldn't work that way. Well, next thing you know, they have to go figure out the theory of that, which they did. But it led them to other stuff that led them to other stuff that led them to this. So there were a lot of models out there being worked, and some of them were weird, and many of them disagreed with one another. Nobody could really kind of come to a consensus. And one of the leading ones at the time that actually kind of works in ways was this drop model of the nucleus. And basically, it treats the nucleus of the atom like a drop of water in configuration. It treats it like molecules inside water, except we're dealing with nucleons. So substitute nucleons for molecules, and you kind of get the drop model. But it had a couple of key features. And first off was surface tension. So surface tension in a drop of water is kind of what holds it together, and the nucleus of the surface has fewer the nucleons on the surface have fewer neighbors with which to interact. So this leads to some sizes of nuclei being stable and others not. So the outer shells kind of being the way they are can lead to stability or not, or sort of instability, if you will, depending on how big it gets. Because if you think about water drops, they can only get big before they start to fall apart. Volume energy. So the binding energy inside the nucleons, inside the nucleus of the nucleons, due to the volume of the nucleus was something interesting. So, they had to kind of hold themselves together with this binding energy, despite a few things that was going on. And that's where the nuclear force comes in. The strong nuclear force is kind of what's holding everything together inside there. And there's a couple more features. So inside, when you have all these protons sitting next to each other, remember protons are all positively charged. So they're going to be pushing each other apart. And the strong nuclear force has to be stronger holding them together than the Coulomb repulsion of two positive charges wanting to go in different directions. And inside the nuclear, that's sort of a push and pull, right? You've got this constant struggle for stability. Well, if it gets too big, right, the nucleus kind of gets bigger and bigger. The Coulomb repulsion wins and splits it apart. That's why, all the radioactive ones are all the bigger ones. I mean, there's smaller radioactive ones too, but in general, the bigger ones tend to be very unstable. You also have this asymmetry energy that goes on. So nuclei prefer to have an equal number of protons and neutrons, and when you have more of one or the other, it leads to instability. again, that sort of push and pull that goes on. Everything likes to be nice and symmetric. It likes to be a certain size. If it gets too big, it falls apart. If you don't have symmetry, it falls apart. You got all these things that lead to these radioactive elements, and that drop model sort of led you to a world where you could kind of figure some of that out, but it wasn't perfect. So, and all that model actually was awarded the 1963 Nobel Prize, and it wasn't until later that this one kind of came into to play as much as before, but as much as that model did. And again, the drop model works in a lot of ways for certain atoms. It just doesn't work for everything. So the fun part about the newer model like this one is it will work in place of the drop model. The drop model is easier to deal with. So if you want to deal with the easier math and you know you're inside an atom that it works for, hey, use the drop model, man. If not, you got to go more complex. So, but it is an incomplete. So in the 50s, there was this new theory that it was presented by these three guys, or one of the two of these three guys, in which there's a difference in between how you treat the inner nucleons and the outer nucleons. So you have these valence nucleons that can kind of move around in certain ways. And if you get enough centrifugal force on these things moving around, you can actually cause deformities inside the nucleus. And those deformities can again cause instability and things fall apart, right? So you like nice stable atoms because otherwise your desk can decay over time, or your steel in your building can decay over time. You like stability. The only time you want instability is when you're trying to get nuclear reactions. So there's times for instability, that's great, but there's also times when you want things very stable. And the reason these models are important is it helps us figure out which world we're dealing with. Are we dealing with the world of stable, or are we dealing with the world of unstable? And can we really tell for sure what's going on? And these models help us do that. So let's dig a little bit more into the experiment that proved all this now that we've talked about the theory. So these experiments, the experiments done to verify this were done in the early 1950s. And Niels Bohr himself was actually alive until about 1960, I think 1962. So I wonder what he thought about his son's work, but the prize wasn't awarded until the 70s. But the work was solid from the early days, and I tried to find some quotes on what Niels Bohr thought about it, but I couldn't find anything solid. But in 52 and 53, Bohr and Mottelson worked on some experiments that showed the way that energy levels inside certain nuclei could be explained was by the assumption that the theory from the theory that they form sort of a rotational spectrum, which is what this model kind of does for you. And the confirmation in between the theory and the experiment was so complete and so perfect that it was just sort of accepted as verification of it. Without having to dig much deeper. Now, what this means, like I said, was if you're trying to figure out which atoms can do what, if you're trying to get a nuclear reaction, trying to get a chain reaction, trying to get a sustained reaction, it's important to be able to model these things out and get the right answer. If you're trying to find a highly stable atom, you certainly want to know that, right? So you need to model these things out and make sure that you got it right. Because if you're trying to build something that's highly sensitive and you don't want it to decay over time, it's important to know. If you're trying to run nuclear reactions, I guarantee you it's important to know exactly what's going on inside there. You don't want surprises in your nuclear physics lab. I assure you, nobody wants surprises in a nuclear physics lab. I've worked in them. Nobody wants surprises in a nuclear physics lab. So this model helped us build a more complete picture of what's going on inside the nucleus. Now, I want everybody to remember, this was just 1975 that this Nobel Prize was awarded. The work was done in the 50s. So it was done in the lifetime of my dad. The prize was awarded inside my lifetime. This was not that long ago. We have not had a very complete picture of what's going on inside these atoms for all that long in the history of humankind. And we're still improving it every day. Now, eventually we found out protons and neutrons were made up of smaller things, right? We eventually find out those are made up of even smaller things. It's possible. I mean, anything's possible. So these things are still relatively new in the history of man, and I think it's important to keep that in mind. So everybody, I hope you've enjoyed this. We'll see you in the 1976 award, and click like and subscribe, and we'll see you soon.